Hi everybody, hope you're doing well. I thought it would be wise to go ahead and start the video lectures with the beginning of Chapter 14 since we had already covered a little bit of that material for the previous exam, but this is definitely going to influence the material on the next exam. I thought it might be nice for you to have it all in video form. So in this lecture, we're going to go back through acids and bases. What are they? And particularly in Gen Chem 2, we're interested in the Bronsted-Lowry definition of acids and bases. So the Arrhenius definition of acids and bases is probably the definition that you were exposed to in high school or in Gen Chem 1. And so the idea here is that an acid is going to be one of those compounds that includes an H, so that you can see how when it goes into an aqueous solution, it is going to produce H pluses. And then the Arrhenius definition of bases are going to be those compounds which contain an OH, a hydroxyl, so that when they go into solution, they are going to form OH minuses, right? And so we're expecting to see some of these compounds with these different either functional groups or different protons on there, and they're going to come off in solution. And so the strong acids and strong bases really kind of fall into that typical expectation for what an acid is going to be, right? So on the left side of each one of these compounds, you see that H. When this goes into solution, we expect that it's going to dissociate, and so you're going to put that proton, that H plus, into solution. And then when we look at these bases, because this is a list of strong bases, we're going to see that OH group in there, and so when this thing goes into solution, they're going to produce OHs. So those fit the Arrhenius definition of acids and bases. Now, we do have quite a number of binary acids on this list, so HCl, HBr, HI are called binary acids because it's just that proton with one other element, that being a halogen. And then we want to note that what you don't see up there is HF. HF is actually a weak acid, so it's not in this list of 6 strong acids or the list of 6 strong bases. So these are the lists of strong acids and strong bases that we would expect you to know. The idea behind what makes something strong versus weak is not that Arrhenius definition. It's a matter of how much they're going to dissociate in solution. So that strong there means that in solution we're expecting that 100% is going to dissociate. So that means that if you had 1 mole of any one of these strong acids like HCl, when they go into solution, you are going to get 1 mole of proton, and you're going to get 1 mole of that counter ion, chloride, right, if we're talking about HCl. And so the same thing with any of these. With nitric acid, we're expecting that for every 2 moles of nitric acid, you're going to get 2 moles of the H and 2 moles of the NO3. Same thing applies to the strong bases. They are strong because they dissociate 100%, and we're expecting that for every 1 mole of that strong base, we are going to get 1 mole of the cation, like sodium, and then 1 mole of the hydroxide going into solution. So the Bronsted-Lowry definition of acids and bases doesn't do that much to change our expectation of an acid, but it does for a base. So an acid under the Bronsted-Lowry definition of acids and bases is going to be a proton donor. And so we saw that for something like HCl, we're expecting it goes into solution and it's going to give us those H pluses, right? So we already knew that an acid likes to donate protons. But when it comes to the base, the Bronsted-Lowry definition updates what our expectation is for a base. There are a number of compounds that if you put them into solution, they are going to cause that solution to be basic or alkaline. And so those compounds don't always contain an OH. So the Bronsted-Lowry definition expands the definition of a base to be any compound that is able to accept a proton. So that H plus has to go somewhere, and if a compound will accept it, then that is going to be a Bronsted-Lowry base. So NH3 is ammonia. We definitely don't see an OH group in this chemical formula, yet this is still going to count as a Bronsted-Lowry base because it can accept a proton. When it accepts that proton, it's going to become an H4, ammonium ion, And so that's the reason why it will count as a base. So aqueous solutions with weak acid are going to be treated a little bit differently than those aqueous solutions with a strong acid. If strong acids dissociate 100%, then we're expecting a weak acid is not going to dissociate 100%. And if it doesn't dissociate 100%, we are not going to describe that with an arrow in one direction saying I'm going to make these two things. We are now going to talk about weak acids in terms of, you guessed it, an equilibrium. It's going forward and it's going back. We said that hydrofluoric acid, HF, is one of the weak acids. So when you put HF in water, that is going to set up an equilibrium where some F's are going to form, some H3O positives or H pluses are going to form. So it'll make the solution acidic, but not 100% of the HF is going to dissociate. It means that we have that reverse reaction happening where the F's and the H3Os are going back to form the water and some stable amount of that HF compound. Same thing happens for weak bases. If strong bases we're going to dissociate 100%, we're expecting that our weak bases are not going to dissociate 100% in solution. I just described NH3, ammonia, as one of those nitrogen-containing compounds, which is classic of a Bronsted-Lowry base. And so in this scenario, we have that ammonia, we put it into water, it sets up an equilibrium such that we produce some ammonium ion and some OHs. So that means that this ammonia comes in, and when ammonia comes in, it's actually going to grab a proton off of water. When it grabs a proton off of water, water leaves an OH in solution, and it's that OH that is going to make this basic solution, right? So ammonia is not providing an OH, but it's reacting with water to still form OHs in solution, which is how we typically think about a basic or alkaline solution. That reversible reaction means that reverse reaction is happening, and so ammonia forming that ammonium ion now can react with the OHs that it formed when it pulled it off of water to go back and form water and go back into that ammonia. So a characteristic of these weak acid and base scenarios is that it's not anywhere near 100%. You might end up with, say, 5% going into H pluses. You might end up with 10% going and forming OHs, right? So it's not a lot at all that is going to dissociate. So just to remind you, we are going to still continue to have participation activities. If I had wanted to do one of those right now, what I would do is I would give you a scenario like this where I want you to draw or describe something, maybe work out a problem, and then it's going to be on a yellow slide like this to call your attention to it. I'm going to ask you to go into D2L, post your answer to the participation activity in the discussion board that's associated with this lecture. Once you post, you're going to be able to see anybody else's response. You can have a conversation about whether your answer looks the same or different than other people's, and then you need to respond within, say, 2 days. I'll make sure that that's very clear when the due date is, so that I can then come back and try to give you the answer that I was expecting, or what I would expect for you to be able to provide on any upcoming exam. But this is not a participation activity, so we can work it together. So in class, I'd already asked you, can you draw what happens with a strong acid and a weak acid when they go into solution? We could have something like our strong acid goes into solution, and it's all going to become HCl in ion form. You're not going to see any H's together with any Cl's, right? So it completely dissociates. So this is going to be our example of the strong acid, and we're going to say completely dissociates. And so the counter example then is going to be that weak acid. We're expecting that it's not going to completely dissociate. And so if it doesn't completely dissociate, that means yes, you're going to see some H pluses and some F minuses, but you're also going to see HF, probably more so than the H plus F minuses, floating around in solution, right? So we do see that we still have some of these compounds in solution. All right, and so we just want to label and describe those differences. All right, so one thing about acids and bases is that when you have that Lewis acid and Lewis base, we're talking about who's giving up a proton and who's accepting a proton. So they kind of come in these pairs, right? There's this idea that, in the beginning you didn't have a proton, in the end you do have a proton, and so that's what we mean when we're talking about acid-base conjugate pairs. There's an acid on one side and a conjugate base on the other side. There's a base on one side and a conjugate acid on the other side. So we've given you multiple different examples here, and we can walk through those and identify what is the acid, the base, the conjugate acid, and the conjugate base. So if we look at this first problem, what we're doing is we're going to look and say, okay, I've got an NO2 on the left, on the right, it picked up a proton. Well, if you can accept a proton, that means that you are a base. That means you had to get the proton from somewhere. You got that proton from water. That means water is going to be the acid. So after the water gave up its proton, it became OH. When it became OH, it became a conjugate base. When we had NO2 accept a proton, it became the conjugate acid. So the thing to remember here is that the pairs are base and conjugate acid and acid conjugate base. It's not base conjugate base. It's not acid conjugate acid. It's base conjugate acid and acid conjugate base. And so if we look at that, it does make a little bit of sense. Over here on the left, our base is still willing to accept a proton. After it accepts that proton, well, now it has a proton that it can lose. Those things that give up a proton are acids, and so we want to call this a conjugate acid, not a conjugate base. The same thing with our acid. When we look at that acid, over on this side it has a proton to give away, that makes it an acid. Now over here on the right side, it's an OH minus. It could accept a proton more so than give up a proton. If you can accept a proton, you're a base. We're going to call that a conjugate base. In the next example, we have HBr, that is hydrobromic acid. That was one of our examples of a strong acid, so that should jump into our mind. That's going to be an acid. After it gives up its proton, it forms a conjugate base, and so that is one of our pairs. And when we look to water, water is what's going to be accepting a proton, so that's going to make it a base. And then once it accepts that proton, it's going to be a conjugate acid. And so that is our other pair. So now we go on to the third example. We've got water and HS. This HS is going to accept a proton, so that is going to make it the base. After it accepts the proton, it becomes H2S. That's going to make it an acid now, but it's the conjugate acid. And then we look at water. Water was going to give up a proton. That makes it the acid. And then it is going to become a conjugate base. So it really is just a matter of looking at both sides and trying to decide who got the proton. We can continue doing this. So now we have H2PO4. We have an OH. We have to decide who gets the proton. We have two H's on H2PO4. It becomes HPO4 afterwards, so it gave up a proton. Gives up a proton, that is going to be our acid. And it becomes a conjugate base. And so by default, our OH is going to be the base. It's looking to accept a proton. It accepts a proton. OH becomes H2O. That's going to make it the conjugate acid. And so that's our other pair. Move on to the next example. H2PO4 this time is going to accept a proton, and so H2PO4 is going to start off as a base. Once it accepts that proton, it becomes H3PO4. That's going to be the conjugate acid. HCl was one of our strong acids, so it should hopefully stand out to us as an acid. And then once it loses that proton, it becomes a conjugate base. Moving down here to the bottom, we have a very strangely written problem, but the key here is that we see that there is an OH right here, and then we move over to the right side, we do not have that OH anymore, right? It's now become another water molecule. So it means this Fe containing ion is going to pick up a proton. So on the left side, it doesn't have that proton. On the right side, it's picked it up. So that means on the left side, we're going to call this the base. This is going to become the conjugate acid. So that's one of our pairs. And then by default, we're going to have this AlH2O, and so this is an even number of water molecules, and so it is actually going to give up a proton, because over here on the right side, now we've got an OH where there used to be an H2O. So that means this is going to be the acid, and then this is going to be the conjugate base. And so again, these come in pairs, and so those are our pairs. In the final example, we have an H on the left side and it becomes an H2 on the right side. That means it is going to pick up a proton, and so if we are talking about picking up a proton, we're going to call it a base in the beginning and then a conjugate acid in the end. That's our first pair. Our second pair, this is methanol, and so this is going to give up an H, which is going to make this the acid, and then this is going to become the conjugate base. And so hopefully what you're noticing as we go through these problems is that it's really about the two things that you mix together that's going to decide what is going to be the acid or base. There are instances where something might be an acid in one scenario and then be a base in the other scenario. And it's all relative to what it's being mixed with and what is going to be a better acid or a better base. And so we'll see that in the next session, and so you can go ahead and close this one and move on to the next section.